lesson of Unit 6, where we'll be learning how to graph and solve a system of linear inequalities. Let's start things off by defining a system. A system is a set of at least two mathematical statements. These can be equations or inequalities. In this unit, we'll be focusing on inequalities. In a future unit, we'll be focusing on equations. A system looks like this. You see this squiggly bracket that's called a set bracket, and then at least two mathematical statements, in this case, inequalities. The solution of a system is the ordered pair or pairs that when plugged in make all of the statements within the system true. So for example, 3, 0 would be a solution to this system because if you plugged it in, you would get a true statement on top, 0 is less than 3, and a true statement on the bottom, 0 is greater than -2. If both of these statements can be made true at the same time from one ordered pair, then that ordered pair is a solution. Now, this may only be one ordered pair, or it could be a large collection, an infinitely large collection of ordered pairs that can make each statement true. Anytime we're talking about the possibility of many solutions, we like the idea of a graph, as that is capable of showing many solutions. The process for graphing a system of linear inequalities is pretty straightforward. It's just going to depend on what we did in the last lesson. Instead of just graphing one inequality, we'll now be graphing every inequality in the system all on the same coordinate plane. We'll also be shading for each of those inequalities. If there is an area that happens to get shaded by each inequality, that will represent the solution set. Let's take a look with an example. These problems can get messy because there's going to be a lot going on to the graph, so I like to be color-coded here. So I'm going to call this my green inequality, and I'm going to call this my blue inequality. For my green inequality, my slope is 2, and my y-intercept is 4. So let's graph that. Starting at 4, going up 2 and over 1, and then I'll fill in the graph with those points. We'll follow our inequality rules here, so a less than means I'm going to shade below, and the line underneath means it's going to be a solid line. So I draw my solid line, and in green I'm going to shade below. The highlighter and notability works really well for this because you're still able to see each of these grid points on the graph. Because now we have to start worrying about the blue inequality. This has a slope of 1/3 and a y-intercept of -1. So now I'm going to graph that right on top of the green inequality. Starting at -1, going up 1 over 3, and throwing as many points on the graph as I can. Now this is a strictly greater than, so it'll be a dotted line, and we'll shade above. Now as you watch me shade, you'll see that there's one region that I'm shading twice, and that's this region in here. These points were shaded once blue because they're a solution to the blue inequality, and once green because they're a solution to the green inequality. That means they're solutions to both inequalities, which means they're solutions to the system. That makes this area of the graph the solution set. Any ordered pair in this area, such as 5, 9, is considered a solution. A point on this green line, because the green line's solid and represents solutions, is technically shaded both green and blue and would be a solution. A point on the blue dashed line is shaded green, so it's a solution to the green inequality, but remember dashed lines are not solutions, they're just boundaries, so this would actually not be a solution. That might be a little bit confusing for some of you, but the biggest thing to focus on is knowing that this area right here is considered the solution set. Now a problem like example 2 is pretty much the same, but might have a little bit more work that needs to be done. For the first inequality, which I again will call my green inequality, it's already in slope-intercept form. I might want to help by putting a little 1 here in front of the x, but that's my m, so I can write that as 1 over 1, up 1, right 1, and 3 is my b. So I'll start at 3 and fill out the graph by going up 1 over 1. This is a line underneath, so it's a solid line, and it's a less than, so I'm going to shade below. Now this inequality is not in slope-intercept form, so we're going to have to manipulate it. I'm going to start by moving over that 5x, and then dividing by -2. Now remember, when I divide by a negative, that I have to flip the inequality sign. So this becomes a greater than or equal to. Now that I've got this in slope-intercept form, I'll call this my blue inequality. The slope is 5/2, and my y-intercept is -2. So I put that -2 on the graph. I go up 5 and over 2, and I keep going until I run out of room. This is again a or equal to, because there's a line underneath, so we'll go with a solid line. And in the end, it was a greater than, so we're going to shade above. Be careful, I know it started with a less than, but it matters what the sign is at the end. So we're shading above, and what you'll see is that area that was just green down here has now been shaded both colors. That makes that the solution set. We want to make sure that we're really clearly showing that we know where the solution set is. So that's why I like to come over with another color and then even label it so that I've clearly shown I know where the solutions are. A couple of quick notes to add about this. First of all, a point over here is only a solution to the blue inequality, when it needs to be a solution to both to be considered a solution to the system. A point over here would only be a solution to the green inequality and not count as a solution to the blue, therefore it's not a solution to the system. Another point I want to make, these areas over here and here are not part of the solution set. They're not part of your real answer. If you wanted to, you could erase these so that only the solution set is shaded. The reason we usually do see these in our final work is just because these problems are often done with pencil and paper where it's not so easy to delete these shadings. It also helps for us to show some of the work that we did to find that area as our solution. As long as this area is clearly labeled, I would always accept this as a final answer. Well, there might not be two lessons all year that are more similar than the last two we've learned. The only difference between these last two lessons is that in this lesson we're graphing two inequalities as opposed to one. Then we're looking for the area that gets shaded by all of the inequalities in the system. We're clearly labeling that area as our solution set, and then the problem's over. If you came away with anything else in this lesson, write that down now. Otherwise, we'll see you in the next unit.